Now we move to the next talk. We stay in the physics, in the particle physics, and now we have Jeremy. Are you there, Jeremy?
Hello.
Hello. Who will speak to us also further about the tracking and about the high energy physics experiment. So Jeremy graduated from Heidelberg University in high energy physics, and at that time he worked for the ALICE collaboration, one of the 4 large experiments at CERN. He was also as a fellowship in the ENFN in the University of Bologna, also in the ALICE collaboration, and since last year he joined us here at the GSI, working with machine learning, applying machine learning technique for track reconstruction for the study of rare signals in the ALICE experiment and in the physics analysis. And Jeremy will speak to us about applying machine learning analysis technique to particle physics. Go ahead, Jeremy.
Okay, yeah, thanks very much for the introduction, and thank you for the invitation as well. It's my great honor to give this talk about some of the ways in which we apply machine learning techniques in the experiments at GSI. So since I assume most of the audience isn't from a particle physics background, I want to start by just briefly outlining what it is we're measuring and why. So generally speaking, in the ordinary matter around us, quarks are bound together by the strong interaction through a mechanism called confinement into baryons and mesons. And the most common ones of these in ordinary matter are the proton and the neutron, which are 2 kinds of baryons. And what we want to do in particle and nuclear physics experiments is to probe exotic states of matter where these quarks can become deconfined from one another. So at the extremes of temperature, we start to see a state known as the quark-gluon plasma, which was thought to exist in the early universe. And at very high baryon densities, we get high-density quark matter that we expect to find at the core of neutron stars. And obviously, the early universe and the cores of neutron stars aren't systems that we can observe directly in nature, but we can recreate similar conditions in the laboratory using collider experiments. And the main goal, basically, is that we want to have very high precision measurements of particle production rates and their properties using state-of-the-art detector technology. So these are the facilities that we work with in the field. We have on the left the well-known LHC at CERN, the Large Hadron Collider, and these are the 4 main experiments there: CMS, LHCb, ATLAS, and ALICE, which is the one that I work with. And then on the right, this is an aerial photo of the FAIR collider facility that's currently under construction here at GSI in Darmstadt. So this is a schematic of the ALICE detector, a large ion collider experiment. So protons or heavy ions will come through the beam pipe from the 2 sides, and they will collide directly in the center of the detector here. And we have a series of different detector technologies at different layers that we use to reconstruct these particles and to identify them. And just some of the main ones that I'll be referring to. There is the inner tracking system, which is currently 6 layers of silicon that we use for vertex determination and initial tracking. We have a large gas time projection chamber surrounding this, where charged particles pass through, deposit some energy in the detector gas, and the signal from this is detected. And we can use this for further tracking capabilities and also for identifying the mass of particles via how much energy they lose through the beta block detector response. And then further outwards, we have the time of flight detector, which can measure the flight times of particles with a resolution of about 60 picoseconds. And this also, in conjunction with knowledge of the particle's momentum, lets us determine the mass and therefore the identity of individual particles. And then these are similar schematics of 2 of the experiments at FAIR that I will mention later on. So the condensed baryonic matter, or CBM, on the left, and the PANDA, or anti-proton annihilation at Darmstadt. These are both fixed target experiments, so you have most of the detectors more in the forward region, but it's using a similar principle that we have various different detector technologies working in tandem in order to reconstruct and identify particles. So then this is a schematic of a typical low multiplicity proton-proton collision in ALICE. So from the hits in the silicon detectors or the signals in the TPC wires, we can reconstruct the tracks of charged particles as they pass, as they were created from the collision and pass through the layers of the detector. And then we want to reconstruct these in order to find out what was originally produced in the collision itself. So what we typically do for this is to rely on the unique topologies of the decays that happen in the detector. So one classic example of this is what's known as the D meson. It has a heavy charm quark and a light quark. The D meson will be produced at the primary vertex, so this is the collision point in the middle of the detector. It will fly some distance, typically about 300 microns, to the secondary vertex, where it will decay into a kaon and a pion of opposite charge. And obviously, because it's within 300 microns, we don't measure the D meson directly, but we can measure the paths of the decayed pion and kaon, and reconstruct these back to the secondary vertex, and then use various aspects of the topology of this decay. So for instance, if we extrapolate the tracks backwards towards the primary vertex, we can use the impact parameter, which is how close they came to the original collision, and also the pointing angle between the reconstructed momentum of the D meson and the flight line between the primary and secondary vertices, and also the reconstructed decay length. In addition to this, we have the particle identification from the TPC and TOF, and this is just an overview of the detector responses compared to what we expect for pions, kaons, and protons for both the TOF response and the TPC, and we have a good separation of these identities at a wide range of momentum. Then we can think about slightly rarer and more complex decays that we can reconstruct, and this brings us to the charmed baryons. So this is something that's similar to a proton or a neutron, but with one of the quarks replaced by a charm quark. So these are significantly heavy particles. They're about 2 to 3 times the mass of the proton, and their production probability is very low compared to the lighter species. And one other thing that we can study is whether they originate from a charm quark from the original collision or from a beauty quark. So we have separate contributions with different detector responses that come from this. These will typically decay within a very short distance of the production point. So the lambda C, which is the lightest charmed baryon, decays within about 60 microns, and this is really at the limit of what we can reconstruct in terms of the vertexing resolution of our detectors. In addition, it's a rare decay to start with, and the probability of it decaying into this specific channel of the proton and the K0 short is about 1.5%. So, in addition, we can consider even more complex decays like the omega C0, which is 2 strange quarks and a charm quark, decaying in this decay channel of a pion and then a kaon and then another pion and a proton with a very complex topology in between. So this is an incredibly rare particle, and also the chance of it, if it's produced, actually decaying into this channel is about 0.5%. So we're talking about probabilities on top of probabilities, meaning that our experimental measurements are very scarce, and it's a very difficult one to find. So we can come back to this image of of a proton-proton collision in ALICE. We see there's relatively few tracks in this case. So in principle, we could reconstruct quite nicely some of these decays from the tracks that we have available. But then we come to a more complex problem where if we have a higher multiplicity of tracks in a proton-proton collision, where this can be on the order of hundreds of charged particles that we see, or even a central lead-lead collision where we can have thousands or tens of thousands of tracks. So these are real images of event displays from collisions. So yeah, this is thousands or tens of thousands of tracks produced, and then from a data taking period at the LHC, which is on the order of a month or two, we can have terabytes to petabytes of raw data produced. And what we want to do is to identify these rarely produced signals among all of these tracks, and also be able to effectively suppress the contamination that we get from wrongly combined sets of tracks. So the classical approach to this would be that we take simulations of various variables that we can reconstruct from the decays. For instance, the invariant mass of one of the decayed track pairs, or the impact parameters, or the PID probability. We simulate this for signal or background for each variable of interest, and then we can apply some set of rectangular cuts. Typically, this will be per momentum interval, and these will usually be tuned by hand. The aim of this is that we want to maintain a high efficiency of the signal so that we don't have to make a major correction to get the actual yield out in the end, but also reject a significant amount of the background so that we can reduce our statistical uncertainties. And this is fine for relatively simple decays, but obviously, because we're making a series of one-dimensional cuts, it doesn't fully use the information that we have available to hand from possible correlated sets of variables. And in particular, if we want to measure very low momenta, where a large proportion of the particles are produced, we can relax these cuts in a simple decay like the D0 that I spoke about earlier. But for the lambda C, using this technique, we don't find a signal. So if we want to try and get any understanding of this, we end up having to extrapolate based on models, which then relies quite heavily on a theoretical understanding of the data, which we want to be able to confirm it with experiment if possible. So this then motivates the shift towards multivariate techniques, where instead of tuning single cuts on individual variables, we want to be able to exploit correlations in the feature space to better distinguish the signal from the background. And the way that we use to optimize this, so we've started recently using machine learning techniques in order to simplify this multivariate problem down to a single probability-like parameter that we can then cut on. So what we use for this is the BDT algorithm, where we assign each candidate a weight based on the final node of each of a series of decision trees. And from this, we have the option of either a binary classification of simple signal versus background, or we can start to use multi-class techniques in order to separate, say, background from a lambda C that came from a charm quark versus a lambda C that came from a beauty quark. So the hyperparameters that we typically use to control this are the maximum depth of the network, which we tend to keep relatively shallow to avoid overfitting, the number of estimating trees, and the learning rate. And then we optimize this with a Bayesian iteration technique. And then typically our training sample will be, we perform a Monte Carlo simulation using the Pythia framework of the desired particle decay, followed by Géant, which simulates the passage of the particle through the various layers of the detector and the detector responses. And then we take our background sample from what we call the sidebands in the data. So these are randomly constructed pairs of particles that are from real data but have a mass that's far away from the particle of interest. So the framework that we use to actually make this measurement, so our data pre-filtering, the invariant mass fitting, systematic uncertainties, are all handled by the ALICE physics package. So this is a proprietary physics from a proprietary package from the ALICE collaboration, but it's open source on GitHub. And this is performed generally on the CERN computing grid. As part of this, we use what's called the KF particle package to refit the decay tracks, and this allows us to set constraints on the masses of the individual tracks. The masses that are assigned to the individual particles. So this is a framework that was developed quite extensively at GSI. And then our model training for the machine learning is performed locally on the Green Cube computing cluster here at GSI Darmstadt. For this, we use the HYPE4ML framework, the Heavy Ion Physics Environment for Machine Learning, which is basically a set of wrapper and helper functions that feeds into scikit-learn. The actual training is performed by the XGBoost library. And one thing that XGBoost offers is the opportunity to use NVIDIA CUDA as a driver interface for GPUs. And then using the Tesla V100 cards that are available in the cluster, we get about an 8 times speed up for the overall training performance versus training simply on a CPU. So this is very helpful for getting a quick response. And then one particular thing that's useful with XGBoost is either we can store the model and apply it locally if we are able to download the entire tree of the real data, or for data samples that are too large, we can serialize the model and upload it to the grid for direct application on separate chunks of the real data, and then download the machine learning response afterwards. So one particular thing that we need to be careful of when we're making precision measurements in particle physics is that we don't want to make an overfit of the data. So when we extract our signal, we will typically have the yield as a function of the invariant mass. And then we will have some combinatorial background that we see here, estimated by the red dashed line. So these are just sets of particles that are constructed together but don't actually form the resonance that we're looking for. And then we will have a peak, typically a Gaussian, of our real signal sitting on top of this. So typically we will fit the background first using the information from the sidebands with either a polynomial or an exponential function, and then a Gaussian signal on top of this. Obviously, this relies on the fact that we are assuming that our background is smooth in the area of interest. So if we have, say, an overfitted model where we would either over-suppress the background in the region of the signal, or we would even enhance the background thinking that it was signal based simply on the invariant mass, this would cause issues for how we reconstruct the particle. So what we typically do to control for this is to check the correlation matrix of the input variables and also the feature importance via the SHAP variable in order to see where we can simplify the model and avoid overfitting. In particular, it's also quite valuable to have a reasonably simple model in the end, because then we can be a little bit more certain that we better describe the overall detector response in terms of the efficiency of the selections that we end up applying. So we can simplify for pairs of variables that give the same info. For instance, if we have both the decay time and the decay length of a particle, these are basically going to give the same information, so we can simplify this down to a single one. We can also remove variables that are less well discriminating. And then the crucial thing is that we have to take special care of anything that has a correlation with the invariant mass of the overall particle to avoid the effect that I mentioned in the previous slide. So then what we determine as the efficiency is the percentage of known candidates from an independent Monte Carlo that are correctly identified for a given cut value. This on the top right is an overview of a typical BDT response that we have for a simple signal background training, where the background is shown in blue and the signal is shown in red. And we'll take the proportion of this above some cut value, above the cut value that we apply on the data to figure out what our efficiency is, and then correct for this in order to get out the actual proportion that was produced in the first place. Then to determine where we want to set the cut for this, we don't want to base this from looking at the real invariant mass distributions for every individual cut value, since this could amplify statistical fluctuations. So instead we define this pseudo-significance variable from an expected number of total signal from either a previous measurement or from models. and then the background from real data after applying the cut. So this then gives us an estimate of where our likely best region would be to apply the cut in order to get the best statistical significance. And then this brings me to the final results after the selection. So after making this BDT selection and correcting for efficiency and detector acceptance, we're able to extract a quite significant signal from the invariant mass distribution at the lowest PT region where we were where it was previously impossible to actually make a measurement. The final result is consistent with the overall spectrum from a standard analysis and extends our knowledge of the lambda C particle into a momentum region that we previously couldn't access. And then for the omega C particle, where this is basically the first measurement of the decay channel in this collision system at the LHC, and what we're able to show is that the results from the data are in very strong tension with theoretical models. So our current theoretical understanding of these heavy baryon production is not well described by theory. Similar applications are made in the upcoming CBM experiment at FAIR. So this is for the hyperon decay, the strange baryon lambda, which is expected to be seen in the core of neutron stars. In this case, there isn't any real data yet because the detector is still under construction, but we can perform training still using background that's generated by a model that's independent from the signal generation. And the initial performance studies of this are showing that there's a very strong discrimination between the signal and background, either before the selection in blue and after selection in red. And then this allows us to make a very high purity selection without much loss of signal. And then we can push the techniques also towards multivariate techniques in order to distinguish the initial sources of the particles that we measure. So we perform a 1 versus 1 training of separate models for background, prompt, which is from a charm quark, and feed down, which is from a beauty quark, and we can make a simultaneous cut on these models in order to both suppress the level of background while enhancing the level of feed down production. And this has been successfully applied for D-mesons elsewhere in the ALICE collaboration, and work is ongoing at GSI to extend the lambda C analysis to use this. And then I want to briefly touch on, so not just on the data analysis, but also how we use machine learning techniques in order to calibrate our detectors. So we've recently made upgrades to the ALICE time projection chamber for the upcoming run 3 of the LHC. So the tracking in this new detector is quite sensitive to distortions in the electric field from ion backflow, which can then lead to a distortion of the track that we end up reconstructing in the detector. And the one method that can be used to correct for this is to anchor tracks to the response from other detectors, but typically this requires statistics on the order of minutes to be able to make this correction, while the fluctuations that we're dealing with are on the order of milliseconds. So what we want to be able to do is take a map of measured space charge buildup in the detector and instead map this to distance corrections that we can apply at each position in the detector to get reliable tracking information out. So what we use for this is the integrated digital current, or IDCs, in various regions of the detector, and this can be used as a proxy for the fluctuations of this so-called space charge buildup. So we can either perform a one-dimensional correction versus time using BDTs or dense neural networks, which allow us to correct for effects due to the fluctuating track multiplicity. And this gives sufficient precision for proton-proton collisions. For higher multiplicity collisions such as lead-lead, we need to be able to perform a 3D correction versus the the radial position, and also the angle and Z position. And then this would be performed using a convolutional neural network known as a UNet, which allows us to classify individual pixels and propagate really the local information from each detector region. The current implementation of the 3D correction is shown on the bottom right. So on the top we have a numerical calculation of the fluctuations versus the machine learning response on the bottom plots. So what we're finding at the moment is that the trained model is qualitatively describing the behavior, but is not really quantitatively able to describe it so far. And what we see from this is that really the training at the moment is sensitive more to global effects rather than local effects. But development is still ongoing on this. So for instance, the pre-application of the 1D correction to reduce the global effects prior to the 3D training. And then finally, we can also consider the reconstruction of tracks in the future PANDA experiment. So the forward tracking system of PANDA is formed of 6 separate tracking stations at different positions in Z, which are arrays of these straw tubes. The straw tube itself can only measure a signal in the center of it, but then we can use combinations of these straws to determine better the actual spatial position. So you have hits in each station that have XZ information from the vertical wires, and then the inclination of the track from pairs of skewed wires in the middle. The track segments are seeded in adjacent pairs of stations using a simple neural network, and you have an illustration of the performance of this so far. So the orange track is reconstructed with the black circles in each of the individual pairs of tracking stations with quite high accuracy using a simple neural network. And then we can use also a long short-term memory recurrent neural network to extend these track segments to the further stations. So this was covered a little bit in the previous talk. And initial tests of this are showing quite high efficiency and purity of the reconstruction for 1 or 3 simultaneous tracks in the detector. And then the performance for larger numbers of tracks is expected to improve as the model is further developed. So this brings me to my summary. So it's a hot and increasingly growing topic in particle and nuclear physics to use machine learning at all levels of our reconstruction. So from the initial calibration of our detectors to the track reconstruction and then our final signal selection. We obviously need to take care to use the appropriate models in order to avoid biases in our analysis due to potential overfitting. But used properly, we can extend our measurement capabilities beyond the simple cut-based analysis that we were performing before. And then we have upgrades of the existing detectors and future experiments that will continue to advance our use of these techniques. So yeah, thank you for your attention.
Thank you very much, Jeremy. And now we go to the questions. Not too much. So one question from Ralph. How to estimate the statistical and systematic error of artificial intelligence-based classification bias with respect to reaching a classical 5 sigma, for example, confidence also.
Right, yeah. So typically the 5 sigma criterion is something that we apply if we are discovering a new species of particle for the first time. We can afford a slightly smaller number of sigma, so down to 3 sigma for an established particle species. So the statistical uncertainties, we typically take those from this invariant mass fit, where it's simply the counting uncertainty of the fitted signal over the background. And then in terms of the systematics from varying the cut, I didn't have time to really touch on this, but usually what we will do is around our chosen working point for the cut, we will vary the probability cut that we apply within some region, and then see what the effect of this varied cut will be on the final reconstructed signal. So basically, it's a check to make sure that the efficiency of our probability cut in the Monte Carlo properly reconstructs the effect that we see in real data. And it's quite similar to what we would do so even in the original cut-based analyses, we would perform a similar approach where we would be, instead of changing the probability cut and seeing how that affects the signal, we would be changing these individual cuts. So the approach there is relatively similar to a classical analysis, I would say.
Okay, thank you very much, Jeremy. So, as there are not many other questions, so let's move to the next session of this meeting. Thanks, Jeremy.